Well, hi everybody and welcome back. It is time for some more fun and frolic with burned out amplifiers, and we have a really cool one here on the bench today. This one's going to be a lot of fun. I think I'm going to really enjoy working on it. And what it is, if you can't tell from the top, it happens to be a Marantz Model 1300 DC. Now if I adjust the camera stand here a little bit, see if I can move it and make lots and lots of dizziness for all of you. You can see this thing was, as far as integrated amplifiers are concerned, this was one of Marantz's top of the line, if not their top of the line they ever made, at least in this era. And it pretty much has every little bell and whistle you could want on it. And I think they're pretty rare too. I've never seen one in real life until this one. But of course, and looking them up online, it seems like they only made them for a couple of years. So this should be a fairly rare amp. And I just did a preliminary kind of look through the schematics. And I'm really impressed with some of the design elements in this thing. So I can't wait to get to work on it. This is just going to be your run-of-the-mill restoration video, and hopefully I can get this thing back to its former glory so we can actually take a listen to it, and I'm very interested in finding out what this thing really sounds like. So if that sounds interesting to you, that is our next project, and well, let's get to work and see what we can come up with. Now my friend picked this thing up, and he purchased it from someone who had it with the intention of restoring it. And this, I guess the story behind it is the individual was going to, got started on it and then kind of decided it was a little bit too much, and he decided to sell it. So that's how we ended up with it. You can see that he began by painting at least part of the power transformer, cleaning that up. There is a little bit of corrosion on the back panel, but the rest of the amp is pretty clean. I mean, all in all. I did a little bit of scoping around, and I know that one channel is really bad, and that's this one. Let's see if I can zoom you in on something I thought was really curious here. If I can get it the right angle, we can see it maybe. Let's see if we can get it into the center of the image. Let's see if I can, how far I can get without going out of focus. Let's see, there we go. I don't know if you all can see this from your perspective, but right there, you see this little piece right here? Let me get a, maybe I can get a flashlight on it. We can see it a little bit better. Right here. That is the remnants of a transistor. I don't think I've ever seen one where the three leads are just left in the board and the actual case of the transistor has blown straight off of it. This is the actual silicon die, I think, or maybe, no, this is the heat spreader that's on the collector, I believe. But you can see the transistor just blew right off of the leads in there. I don't know if you can see that or not. Of course, in addition to all this, we have a flame roasted resistor here. And I noticed that the previous owner, I don't know if I can get you at the right angle to even see it, but no, it's kind of hard. You can kind of see down here on this one the X on it, and all four of them are marked with X's, so I'm assuming all four outputs are shorted. Heaven knows, you know, this is direct coupled amp, so probably the drivers are all shot. So I know some of you on the Marantz 250 were kind of not wishing badness upon me, but I think some of you were hoping to see the drivers and so forth being burned out on that and how I deal with that. Well, I think you're going to get your wish on this one, because these are all going to get replaced. This uses a very unique front end. It uses a set of those matched transistors. It's strange, but they're all over the place inside here. The original ones, and these are original. I mean, they were factory, but you can see down here with the heat shrink, the differential pairs, and you can see even like in the preamp stage, there's one down here. There's another one over here. You can kind of see. So all of these differential pairs are thermally coupled with heat shrink. However, this is a lot like the Pioneers from this era, where it actually has the silk screening and it has the layout that you can optionally use the dual differential transistor pairs. And I have a few of those in stock that I've been saving for a rainy day. I don't use them. I may put those in this one because I think this is going to be a nice amp. The other thing they're using is, I don't know if you could see it down there, but an integrated circuit. And this integrated circuit right down here is actually two JFETs, two N-channel JFETs. And those are used as the current source for the diff pair, if I'm not mistaken. And I have some of those too, by the way. Those are a little more common. You can still get them. But anyway, long story short, I'm going to go over and I'm pretty much going to replace all the components in this thing. I'm going to really go over it with a fine-tooth comb and kind of rebuild it, clean it, make it nice, and then we're going to just see how it works. So I'm going to get to work. We have a lot to do. We're going to start with these modules. We're going to pull them out, and well, we'll see where this adventure takes us, huh? Okay, module number 1 is out, and I have to say it took all of about a minute and a half. This has to be one of the easiest amplifiers I've ever disassembled. Essentially, you take these two screws here, this one screw here, the whole thing lifts up. The wires are actually long enough, as you can see over here, to reach, and you can just reach through here and unplug them. This is your input wire, this is your power, and then this goes to the overload circuit, I believe, or to the low voltage power supply. We'll have to look it up in the schematics. Everything is pluggable on this heatsink. In other words, if you look, you have these connectors on the board for the main power transistors. So when you remove these screws, this heatsink is separate. Okay, I don't think it's coupled to the actual main heatsink. And this will unplug, so the transistors will stay on their sockets on the heatsink, and the whole board just kind of unplugs. We just take this screw here and these screws around here, the whole thing comes off. So this is going to be very simple to break down so that we can rebuild it. Okay, you're going to just see a bunch of little clips that I'm going to take here, and I'll leave them in the video. And they're just kind of notes for myself as I'm disassembling this, and some things that I'm noticing. I'm going to make some notes in the video. As you can see, here is the transistor that's for the thermal tracking. I think this is part of the bias circuit. Again, I might be wrong. But notice how it's just kind of floating in between the two fins of the heatsink. It's not really mounted to anything. I don't know if that's the way this is intended. It looks as if it's not been interrupted. And again, having not worked on one of these models before, this is all new to me. So just wanted to take note of that. All right, let's finish taking these apart. Okay, and this just pops right off, and you have your 4 connectors going to your 4 transistors, and then we'll clean this really well. And that's just how simple it is, how it comes apart. And here's our board. You can see this sticking up, and the main thing I was concerned about was burned up tracks. And just kind of taking a first peek at it, I don't see any burned tracks, although some of these traces are very, very thin. So we're going to have to be very careful. This looks like the type of board that these traces will lift right up off the board if we're not careful. So we're going to use extreme caution when we're working on this board. Another thing another note here. Even though this has heat shrink, almost like there's two transistors fused together in there, looking down here now at the shape, I think this is an original, forget what number it is, I'll put it up on the screen, but one of those encapsulated dual transistor modules. This is an actual one, so I will probably still replace it because these things are notorious for shot noise. So these are going to get replaced. I may replace it with a modern, with a new old stock one. Or I might make a set of matched ones. I don't know yet. We'll see. But that's it. So we have, what is that, a big old crack there? No, it's crud. And we have, there's where our transistor used to be. Look at that. That's crazy, isn't it? Blown right off the board. And then we have this resistor and this resistor cooked. So we're going to look that up on the schematic, and we'll see exactly what those connect to and why they fried. Of course, the outputs are bad, and we have to go through and check all the drivers and everything as well. So really, really unique design. You can see all these little transistors that are thermally coupled together on this little heatsink module here. This, and even one of these little varistors or thermistors, whatever you want to call it. And they're on a heat spreader that's connected to the emitter resistors. So they're thermal tracking with the emitter resistors. Again, I've never seen anything like this laid out. This is fascinating. Really, really interesting. All right, let's just check a couple of these components out. All right, with any luck, we are in frame. And everything's all visible. Okay, we're on diode check. And let's go, I think it goes emitter collector base, or does it? Yeah, emitter collector base. So base is here, and this is a 2SB, so that should be an NPN. So let's check from here. So base, that's open from base to collector. Base to emitter is reading something. And then emitter to collector. Yeah, I don't know. We might be reading across things, but I don't know. Let me see here. Let me go this direction with it. Okay, there's my drop there. And that's, yeah, this is bad. Even, I mean, we're probably reading across some other components, but still, I think we're not good. Okay, so this 2SD. Okay, we got something there. Dead short. That one's shot. Whoa! Take a look at that one. That one is just blown apart totally. I don't need to test that. And this resistor is fried. It is just amazing that this board did not melt down. The components all failed and dead shorted, but nothing. So I'm convinced that I'm going to do an absolute wholesale rebuild on this. We're not going to test anything more. Other than some of the most basic resistors and things, this thing's getting stripped and everything's getting replaced. All right, let's do emitter to base on these. So emitter base, open in both directions. Open in both directions. Open in both directions. Open in both directions. Okay, now collector. That's no good. Dead short. Dead short. Almost dead short. So, everything is fried on this channel. So there you go. Now I know the previous owner had this board out and checked a few of these things, I'm pretty sure. Because you could see there were some markings put on here. I got a little bit of rust here. We're going to have to clean that up. Nothing terrible. All right. Get to work. Again, I have not turned this thing on. I'm not going to. Looking at the power supply, you can see that there are failed capacitors in there. If I go down here to this one, you can see that it's really bad. Right here, all corroded and everything. Good grief, it even looks, yeah. It just completely leaked and came apart. So this whole amp, I mean, all the parts on it are just completely shot. So as they say, the journey of 1,000 miles begins with the first step. And of course, we always start at the bottom and work our way up. And at the very bottom of everything, at the very beginning, is your power supply. If we don't have a good power supply, the rest of it doesn't matter. We can't test it, nothing like that. So I am going to remove the power supply board. I'm going to check all these capacitors very carefully. And we're going to make sure all of this is correct before. This is the protect board, by the way. This is the power supply back here. Take all this out, rebuild it first, get it working, and then we're going to do the amplifiers. And we haven't even begun to look at the preamp section. It's all intact. That's what counts. So we're happy for that. Okay, flipping the amp up on its side, I've removed the bottom cover. And what we want to do is kind of inspect the power supply. As I said, we're going to kind of start at the beginning and work our way through. I've removed all of the boards and essentially that, well, at least the boards that are around the power supply. I removed both power amplifier modules, the power or the speaker protect board, and the regulated power supply board. And these capacitors are, as you can see, they've all leaked. They're really in bad shape. So we're going to replace all of those. We have all new components. We have to kind of check all of these resistors. Some of these bleeder resistors on the capacitors, this one in particular, looks a little bit crusty. I don't know. Maybe it's just the way it is. We're going to check these capacitors. Typically the caps are good in a lot of these, but this amplifier, almost every board, the caps look swollen, and I don't know if it was just bad caps that they used in here, or if this thing was subjected to some kind of environment that caused them to fail like that. But regardless, we're going to go over these. I'm hoping I don't have to replace these, because that's going to be a lot of extra money for this restoration if I have to buy these 4 10,000 microfarad 80 volt capacitors. But if that's what we need, that's what we need. So we're going to start, and I'm going to apply power to the transformer, make sure we have power to that, and make sure we have a rectified, unregulated voltage, for your DC rails. And then we'll move on from there. Okay, with all the boards out, we're going to check this transformer. And we have our 2 sets of windings, and they're both referenced to the chassis ground. So we're going to look at our positive and negative for left channel and positive and negative for right channel. I am connected over here to the dim bulb, and I'm going to put on my noisy buzzy isolation transformer. And now we're going to turn the power on, and let's see if we get our, through the bulb, I'm not sure, there's going to be some voltage drop there, but should be somewhere around 60 volts. So let's see what we get. All right, so our light flashed on and then went dim. And as you can see, we have our positive 57 volts. I'm going to try not to short anything out. Let's go over to the other side. That should be our negative 60 volts, and it is. And let's go over to the other side, which is going to be right here, negative 60. And this one should be the positive 60 for the other channel. And it is. Okay, so let's take this off. And let's go to AC, and we'll look at the low voltage power supply windings, which are up here, and I'll try not to short them out. Okay, so there's 36 volts AC to that side, 36 volts AC to that side. So our transformer's good. I'll shut that off, and we'll let that bleed down. And the good news is everything is working there. Now again, we don't know the condition of these 4 big capacitors, but we'll test those later. But we know we have a good transformer, and that's really the most important part of this whole amp, because that's really the expensive and difficult part to find. And you can see how they painted it. I'll shut this buzzing transformer off. You can see how they kind of painted the top part of it. So it kind of looks okay up there, but kind of masked it off. I don't know that I'm going to, I don't want to unwire the transformer to remove it and to be able to paint it better. So I think I'm just going to leave sleeping dogs lie with that. And I'm just going to clean around it. All right, we have the amplifier sitting aside, and I'm just brushing some evapor rust onto the rusted areas of the chassis and kind of letting it dissolve the rust a little bit and dry. And then I'll go through and clean that off after several applications and waiting a couple of days. And while we're doing that on the side, we're going to start rebuilding the boards. So the first one we're going to start working on here is the power supply board. And I'm just going to replace all the components. And I know a lot of you ask what I replace what with. So we'll just go through. For the big transistors, the originals are Sanyo 2SB507 and 2SD513. And what I'm going to use is a 2SA940 and a 2SC2073. And those are going to be very similar. Those should be good replacements. These larger transistors here, the 2SC1509 and the 2SA777, we're going to replace those with a KSC 2383, KSC 2383, and a KSA 1013. These are just things I have in stock, so they were the closest match and they'll work. The smaller transistors, there are a couple of JFETs in there. I'm not going to change those. Those are the 2SK30As. I think they're okay. But the other small transistors, there are, let's see, there is a 2SA970 and a 2SC2240. And what I'm going to do is for the 2SA, I'm going to use a KSA 8 or KSC 18. I'm sorry. Let's go back. The A, which is the 2SA 970, I'm going to use a KSA 992. You can see all that. And for the 2SC, which is the 2SC 2240, I'm going to use a KSC 1845. So just replay the video a couple times if I confused you on that. So that should do it. And then we're going to replace the capacitors, which are very badly worn. You can see they're corroded and they're swelling. You can see this one pretty bad. You can see they're opening up. This one's all puffed up and both of them are and popped. So I'm going to replace them. I do not have, these are all four 1000 microfarad capacitors. I do not have a 1000 at 35 in an axial lead like that. So I have all 1000 microfarad at 50 volt, and they'll work just fine in here, and they should not have any problems staying formed up and so forth. So we're going to replace those. They're Illinois capacitor, pretty decent, 105 degree, pretty good caps, so they should be all right. All right, let's get to work. And then, of course, these small caps, we're just going to replace those also. With whatever I have some Worth and some, I think some Nichicon PW series we're going to use. So let's get to work on that. And then we're also going to spot check all of the resistors and make sure they are good while we're in there. Another thing we're going to test and look into is this variable resistor. It's a 4.7K. I might leave it alone, but we'll see. Maybe we'll do a little soldering chat, and then we'll end this part here, and we'll have to wait for the amplifier chassis to finish drying and everything before we can come back and actually put this back in and test the power supply. All right. If you can pretty much skip ahead or whatever if you don't like watching all the soldering, boring stuff. Some of you like that, so we'll do it. All right. Let's pop these fuses out, and I got some new fuses, and man, our fuses getting expensive. Everything's getting expensive now. Just everything costs so much more than it did even a year or two ago. It's just crazy. I don't know. So the first thing I want to do is I want to make sure that all of the markings are correct on the capacitors for the positive. And I'm going to remove them because they're kind of big and in the way, and then we can clean the board off a little better. So I'm just scraping this glue off. This, again, this is that brown glue. Some of it really messes up, and you can sometimes put some isopropyl alcohol on it. It'll help soften it up. Sometimes it doesn't. Right now, I kind of like it like this because it stays together and you can kind of get it all off in one chunk. But this stuff can be corrosive sometimes. Some of this glue will just eat at metal, especially the leads of components, and it'll just trash them. So, and again, this is a matter of convenience. When they made this stuff, they would, you know, glue these components down before they'd run them through the wave soldering to make it stay together. Other times they would put this in here because the component sizes were much larger at the time than they are now, as you can see, and the weight of the, you know, of that component rattling around in, you know, transport when it was being shipped would quite often work the component loose from its solder pads on the back of the board, which is not a good thing. It sometimes even lift the tracks off the board. So they would glue them down like this. So I guess the intention was good, but the result was not so good, you know, after some time. And let me see if I have a better tool than this. I have one of these little X-Acto knives, and you can get these little X-Acto chisel blades, and they're very sharp. And I use them a lot for this, because sometimes it does a little bit of better job of scraping off. Sometimes it doesn't. Like this glue has hardened. It's not as pliable as it originally was, so it's a little bit more difficult with these little flexible blades. They're flimsier, but these can get underneath sometimes and scrape. But anyway, clean that off, and then we'll take a little bit of alcohol maybe and clean it. Let's see here. Some isopropyl. Okay. Just kind of clean all this gook off of here. And there is some paint overspray on these fuse sockets from when one of the previous owners painted the transformer, but doesn't look too bad. I don't want it to be on these, I don't really want it to be on these terminals where the fuse goes. On the outside, I guess it doesn't hurt. So let's take a little bit of acetone, and some of you guys are going nuts over the solder in chat, but well, not for you. Probably should watch something else or skip ahead. I like watching people work like this. It's kind of relaxing, and you never know what somebody's going to say. So I kind of tend to watch videos like this. You know, you don't always need to be 100% learning something all the time. I think that's the problem of this world right now. Some of us are too busy. If you're too busy to relax and have fun, you're too busy. I know we all think we have to be that busy all the time because we need all these things, but I don't know. The older I get, the less the things start meaning to me. You know, like all these stereos, they're fun to fix and they're fun to listen to and to test, but you know, you only really need one. Although I have a lot more than one. But I'm going to start getting rid of some of them. I actually have started getting rid of them. I've gotten rid of a few, given quite a few away, and some of them I even gave away to some of my patrons. A couple out there that I knew they would go to a good home, that they would be appreciated. Well, that cleaned that up a little bit. Certainly better than it was. I just wanted to get that paint overspray off of there. There we go. So I'm just using basic acetone or nail polish remover, whatever you want to call it. And if you're careful and you go really quick, it won't take the silk screening off the board, you know, all the lettering and so forth, but it will take the paint off. And that's kind of what I wanted to do, is get rid of that paint spray. So that looks better. Much better. Okay. Like I said, I really want to clean this one up if I can. Do a little bit neater job than I normally do, because I really like this amp. I think it's a pretty rare one. I could be wrong. Maybe there's a lot of them out there, but I don't think so. And I just want these to be as good as possible. All right, so let's replace these transistors. Let's do that. So I'll desolder them first. And again, they may be still good. I don't know, but looking at how burned up that amplifier was, you don't know what this thing's been through, and you don't know if these transistors are going to start leaking or, you know, shot noise or something like that. Especially when they get up to temperature. You can see how big the heat sinks are on these. So these are designed to dissipate, you know, a lot of power. And so definitely want to make sure that they're, let's see here, get that cleaned off, make sure these tracks are all good. We'll clean this board really well and soak it with alcohol to kind of spread all that excess flux and everything that's under there when we're done. Okay, so take this one off. These heat sinks are tapped, so there's no nut on the other side of this, which is pretty cool. And we'll lift this one up. And if the pad's good, we'll reuse it, and if not, we'll replace it. I think the pads look pretty good. I don't think these have ever been taken out or messed with. Okay. Get a little paper towel. Again, I don't know when I edit this, you know, take a couple things out, we'll see. All right, let's see how this thing tests. We'll just give it a quick check here in the transistor checker. So it's a PNP, and you can see very low HFE. All right, let's see what this 2SA does, or the KSA, I'm sorry. It's probably going to have a lot higher. Yeah, it does have a higher HFE, but I think that's not going to matter on this one. We'll see, though. Hopefully, we will be able to adjust it. And I also want to check the Zener diodes in here that are used, because I think there are a couple in the circuit. I'll need to print out the schematic and verify that, but we'll take a look at a neat little piece of test equipment that you can buy online, like eBay type place, AliExpress, whatever. And it's really not intended for this purpose, but it actually works really well for this purpose. And I'll show you it here in a minute when we go to check all of the Zener diodes. You just have to kind of be careful with it, because you can get zapped on it a little bit. Again, we'll talk more about that when we get to that point. All right, I just want to clean this. There we go. All right. So let's see, little pliers here. Go kind of like that, I would say. Make sure they're lined up properly. Yeah, not too bad. I probably should go a little further down than that. Measure once, cut twice, huh? I think that's what we just did. All right. And I'll put this down in there. Okay. I'm going to switch to my nice bench glasses, because they really work for this. I love them. Okay. Let's take this out. And let's get our heatsink goo. And let's grab one of these and see if we can get grease all over ourselves today. There we go. Use another cup of coffee this morning. All right. There we go. And then we'll clean it up later. Okay. Put a little dab on there. You don't want to use too much of that grease, because it can actually insulate the heat if you put too much, believe it or not. Just enough that you can see it on there. Everybody has their own little opinion of how much is enough and how much is too much and all that, but and look what I did. I still didn't bend those down far enough. And looking at this one now, you can see how tight they had that, so that's not good. So let me get this off. Has to be right. You don't want it to short, that's for sure. So let me straighten these out. You really shouldn't bend these a whole bunch of times like this, so don't do what I'm doing. Do it right the first time. Okay, I'm going to bend these down towards the tabs a little more. Put this back on here. Try not to make too big of a mess. We used to have a lot of power supplies like this at work that we would work on a lot and have to, you know, replace transistors and, you know, the LM78 and 7900 series regulators and all that. But today, you just don't see as much of that anymore. Everything's all surface mount and switch mode power supplies, and you really don't get into this stuff as much. Although there's places, you know, where you still have to know all this. And I'm thinking, I have a new employee, and I have some of my employees I've had for a while. And I was thinking for them of posting some for review and for some of the new guys, some basic electronics videos that really aren't audio related, which is kind of not like this channel. And I may just leave them private, but if enough of you are interested in it, I will make them visible, because I really don't have a problem doing that. But doing a basic video on electronics, like Ohm's law. I'll start out with like Ohm's law, and then how to test, you know, with a multimeter. Very basic things like that that most of you that watch this may already have known for a long time, or may know enough about, or may not be interested in because you just like seeing me fix stereos and playing them on here. But for the new people that are new to electronics, or those who play with electronics but never formally got to learn a few things, I may do that. And again, it will by no means be a, you know, university level class, but just the basics, what most of us know and do. And I'm just kind of thinking of doing that to help them along a little bit, because sometimes the guys get out there and get to work on something and they really get into something a little deeper than normal, and it's nice to know some of those things and to know the basics. So I think I'm going to do that. I'll do one on Ohm's law, you know, volts, ohms, and amps, and watts, and all that. I'll do one on multimeters. I've done some scope videos already, and I may do some more specific scope videos to what kind of things we do at work. May not make total sense to all of you out there, so again, I don't know if I will post them or not. We'll see. But yeah, let me know if you're interested in seeing them. And that there may be a lull in the audio videos on and off as I do those basic ones. I'm going to try to keep them short and to the point. So we'll see. Let's see what this one is. Should be an NPN. Yep. Another low beta. Again, there are other transistors out there that we could probably use that have lower beta than these. Matter of fact, I bet this one's high also. This is NPN. It's going to be probably in the mid hundreds. Nope, it's low. Okay, it's a little bit lower, but these will work. These should be just fine. I'm going to try to get these bent the correct way this time. You know, okay, that's good. So we can clean this one up too and reuse it. I could also use sill pads. I have some very nice sill pads, but I'll just keep this original. We'll see. It should work just fine. It worked all these years, didn't it? So we'll just keep everything as is, unless I crack this thing. Which, nope, it's turning out okay, cleaned up. Okay. All right. right, let's put our stuff on. Oh, I didn't clean it off, did I? Getting ahead of myself. Why didn't you all remind me of that? As I shoot isopropyl across the bench. There we go. Much better. Okay, now we can put this stuff on there. So I get the hair out of there. There we go. Nice. We have been working with a new product, and it has been quite a challenge to kind of get the software where we like it and the image quality where we like it, and it's actually going to be a really cool thing when it comes, you know, when we really get everything finished. But tell you, the imaging industry is changing, and for the better. I mean, I almost can't believe how tiny amount of radiation you need now to get a very good quality, like superior quality image for the radiologist to be able to read. It's almost, I had to kind of step back and accept the fact that things have changed and gotten that good, because it was one of those things where I thought, you know, this is the laws of physics, they're not going to change, and we're, you know, and the laws of physics haven't changed, but our use of the laws of physics have gotten a lot better, is what I should say. And it's pretty cool. You know, in the old days, we would make, you would take an X-ray by, get this, using a standard piece of black and white film. So the film would be exposed by a phosphorescent screen, and that phosphorescent screen would light up when X-ray photons would hit it. So you had your phosphor screen, or they sometimes called it the intensifying screen, inside of a cassette. And that cassette would have a screen on either side of the film, and then when the X-ray would strike it, the screen would glow either green or blue depending on the material they used, and it would expose the film, and then the film would be developed, you know, in a processor, and that's how you would see the radiograph. And of course the idea of an X-ray is X-ray photons, depending on what kind of energy you put into them, they have the ability to penetrate certain densities of objects and be absorbed by objects of less density than that, if that makes sense. And so, you know, since bone is more dense than tissue, your bone would absorb the radiation and your skin would pass the radiation through, and you'd cast a shadow of that bone onto the X-ray film. And it's very different how we do it today, because it's all done digitally. There's no film involved, no processors or chemicals or anything. You have what's called, well, without getting into direct conversion versus indirect conversion, most modern X-ray detectors have a scintillator, we'll call it. And it's called scintillator because it scintillates when a X-ray photon strikes the array, the scintillating array, which is either going to be gadolinium oxysulfide or cesium iodide. That cesium iodide, or gadox, whichever, will scintillate. It'll glow. It'll give off little glowing dots. They're very tiny, microscopic. And then that scintillating layer is fused to a TFT array, or a thin film transistor array, which kind of acts a little bit like a CCD camera, but not. It's similar though. And it will convert the optical light that is produced by that, by that cesium into an electrical current that can be passed through a little preamp, and then you can actually create like a kind of a z-axis brightness signal. And of course the pixels will have an x and y coordinate, so you have an x, y, z array. And then that can run through some computer algorithms, with some lookup tables, and it becomes an actual X-ray. And, when the first ones came out many years ago, I remember it, they were extremely expensive. I mean, just the detector, not even the X-ray machine to make the X-rays for it, just the detector by itself. It's upwards of $250,000 for one detector. Of course, each room usually needed two detectors, one in the table and one in the upright stand where you would X-ray your chest when you're standing up. And I remember the day when, they released a $100,000 detector, and that was like this huge bargain basement price, and it's going to revolutionize everything. And, and now the price has dropped even further, and, detectors are a fraction of that now, but they're still very expensive. And the efficiency has gotten so much now that X-ray machines weren't really designed to put out that low of X-ray for certain anatomy. And it's pretty amazing how just the tiniest amount of X-ray can get a beautiful looking image. Unlike anything we've ever seen before, and you have the ability to window and level, to zoom in, all kinds of different things. You can invert the image, black and white inversion, all kinds of amazing things. And it's just really amazing. Okay, so I gotta wait for this to warm back up. So we've been really, really busy with all that. And that's why I haven't had as much time at the bench as I'd like to have, And so sometimes in the morning before work or in the evening before bed, I'll come down here for half an hour or so, and that's about all I can get. But it's all good. I mean, I love what I do, and nothing would make me happier than to see my employees get to a point where they can take over one day. Okay, so there's our PNP, and it's emitter collector base. So ECB, and it's written on this thing like that. And let's get this 2SA. And this is going to probably, again, have a higher HFE. It does a little bit. And it's ECB. Okay, so has the same pinout. That's good. Always check that. And we're going to put this in. What I'm going to do is I'm going to heat up this center post a little bit, just to get it seated, and we'll snip our leads. So sometimes when I'm at the bench here doing things, I'll use some terminology that may not match what you use either in regular standard electronics or in the audio industry. And some of it is because we used sometimes different terminology in the X-ray industry. And that's what you're hearing me use. A lot of times, instead of milliamps or milliamperes, I'll call things MA. And a lot of my foreign viewers don't know what a MA is. And I know that sounds kind of bad, but but that's what it's called in our industry, because the way you measure X-ray, at least in the clinical field, is you rate the X-ray quality or its type by the amount of current that is flowing through the X-ray tube and the amount of voltage in kilovolts that is being applied across the tube. And the current flowing through the tube is in milliamps. So it can be anywhere from 1 milliamp or even less in some instances to over 1 amp. And the voltage can be anywhere from 40 kilovolts up to 150 kilovolts. And yeah, 150 kilovolts, there are, not anymore, they don't use them because we don't need that kind of energy anymore, but there were machines that could produce 150 kilovolts at 1 amp. That's a lot of power, and I certainly would not want to get in touch with that. I've only known one person that ever got directly hit. Because of all the interlocks that these machines have, it's very hard to get shocked by that, the primary voltage like that. But, or not the primary, that's a different thing, but the actual, power that's across the X-ray tube. But one person got it in their hand and it arced out the back of their elbow. And it literally blew their elbow out. It's very ugly. Not anything to play with. So that's a story I share with the new guys sometimes when I go to work on this stuff, because it'll kill you. I mean, if you get across that, it'll kill you instantly. And then the primary voltage that drives all that is quite often 480 volt 3-phase power, and you can have a 100, and some of them even have up to a 200 amp circuit breaker, especially like some of the CAT scanners out there and so forth. They're no joke. And it's kind of what we work on every day. So you have to be careful. It's a little different than working on these kinds of things. I mean, of course, you're working with mains voltages with these too. You should always be careful, but you start working with industrial voltages like 3-phase power and so forth, it's not good. So let's check this. I'm mainly making sure the pinouts are the same. So this again is ECB. So we're going to use this is the 2SA 970. We're going to put the KSA 992, if I can find it. There it is. So here's our KSA 992. Yep. All right. A lot higher gain again, but I don't think that's going to matter on this one. If it does, we can pop it out really easily and replace it with a different one, but I think actually going to be good. And I actually think that the beta of these transistors was a little bit higher on them when they were brand new. Sometimes the beta can actually go down as a transistor ages. Not always, but in some cases that will happen. And they'll still work, but they just don't have the same HFE. Now, because of the way that the circuit is designed and the way that it's biased, sometimes the gain of the transistor isn't as important because the circuit isn't dependent upon the beta of the transistor as much. And in that case, then we really don't care if the transistor has a little more or less gain. Again, it's all about the design of the circuit. It's really what it comes down to. Okay, there's our 2SC 2240. Y'all bored yet? So yeah, I mean, I don't talk about the X-ray stuff a whole lot, but I thought you'd be interested in knowing that and some of the things that are out there today. It's really amazing. And so the technology that goes into, when you go get an X-ray is, a lot of times you just kind of take it for granted. You go in there and they go on this machine and it just works, But there's a lot that goes into it, and you have the service engineers, such as ourselves, that install and maintain the equipment. And then you also have the radiation physicists who come in and they verify and validate our work. So, when we do work, we are inspected. And of course, the owner of the equipment would be the hospital or the imaging center or whatever. They are responsible for making sure that they call us in to do our jobs and call the physicist in to do their jobs. And so there's all kinds of checks and balances in the industry with that. And, of course, the news media always likes to make up their own story to get you to look at their crap, which I hate. I'm not to say that the things don't fall between the cracks. I'm not saying that there aren't unprofessional people out there, but it's a lot harder for that to happen than a lot of people may realize. And most of us out there, not all of us, but most of us out there, the vast majority, absolutely take our jobs very seriously, and we care about you and your family, whomever it is that's going to go in there and be treated on these pieces of equipment. We understand that what we do does make a difference in your health care. I mean, if a doctor can't see something, it's very hard for that doctor to be able to properly treat you or to diagnose you. And it comes down to the equipment that doctor uses. And if it's working at its proper specification. So, yeah, we take it very seriously. And it's something I demand of my employees. And we love to go have fun. We love to joke around and all that out there, because it's some of what we do and see is stressful and busy. But at the end of the day, we all know what we're there for. We take it very seriously because we know that it could be anybody on there. It could be our own family or friend. But even if it's not our family or friend, everybody's important. And we want them to receive the best care that they can. And that's what it's like to do this kind of work. And some people, they just have a natural affinity for this type of thing, and they do very well in this industry, and some people just don't. It's a personality thing. Okay, this capacitor is 100 microfarads at 10 volts, and I got originally a 10 microfarads at 100 volts. That's not right. So I had to go dig this one out, which is good. And this is 100 at 10, so it is the proper component. And we're going to, and when the lead spacing is off, it's always good to kind of give them a little bend to the leads like that, so that you don't put a lot of undue stress on where it goes up inside the capacitor. All right. So you might ask yourself why if you work on this stuff all day for a living, why would you want to come home and do this? Well, I really like the audio. I don't see this in the same as what I do at work. I mean, yes, it's electronics, but it's so different. And it doesn't have the stress. I mean, this is all about enjoyable, happy things, and which is good. And I also do the woodworking. When I go down the shop there's no electronics, no internet, no just me and the woodworking tools, which is also very good. I mean, working in the medical industry in general can sometimes be a bit stressful. And, one of my friends was an ultrasound engineer. He worked on the ultrasound equipment. And, he worked in the obstetrics department sometimes. And he says, you want to talk about stress? He says, you're the guy. You have to walk through a waiting room of a bunch of pregnant women with full bladders, and you're the thing that's preventing them from getting the procedure done until you get it fixed. So he's like, yeah, that's stress. Funny story. I was in a mammography mammography department. That's breast imaging. And this was very early in my career. This was like in the late 1980s. And I got called out to work on a mammo unit. And wheeled my toolbox into the room, through the waiting room and all that. And I stooped down. I had a pair of Bugle Boy, trousers, khaki trousers on, and stooped down and ripped my pants from stem to stern. So here I am with a big hole in my pants, my underwear sticking out, and I have to walk back through that waiting room. Yeah, I called the office and said, sorry guys, I'm going home now. I'm done for the day. So yeah, that was fun. Lots of funny stories. All right, so we got these done. Let's lift the leg of this diode right here and see what it is. This is a Zener diode, and we're going to use a little piece of test equipment I picked up a while back, and it's really cool. Of course, you've all seen my, what is it, Peak Atlas, or whatever the name of the company is that makes it. You've seen this, the Atlas Zen, which is like a Zener diode tester. But I'm going to show you another one. It's a lot less expensive, and it can test Zener diodes of just about any voltage rating, even the higher voltage rating ones that you don't see very often. Let me go get it. Let me put my microphone on. All right, so what we have here, this is called an LED backlight tester, and the whole purpose of this is to be able to test the backlights of LED or LCD televisions. So all these LCD televisions, they have to be backlit, and a lot of them, there's cold cathode lighting, and then the later ones use an actual LED array, so a bunch of LEDs. And they can run, in the hundreds of volts, because there are a bunch of LEDs in series. And what this thing does is it will test them to, number one, see what the voltage drop is across the LED array, and number two, show you the current through the LED array. And it's current limited, so the maximum when it's set to large current is 40 milliamps. But in small current, it's only a few milliamps. It's not a whole lot. And what's nice about this is open circuit. When you turn it on, you can see it has about 228 volts open circuit. It can have a little more than that in it, once it gets up and going. See, it says 320 volts. It's 323, and I don't know if you can see that with the lights on. Let's turn the light off here overhead. Maybe you can see it better. And you can see the probes are covered. And the reason is, right now, the open circuit voltage on this is 323 volts. So it could give you a fairly good zap. So you do not want to touch the probes. But the nice thing is it's current limited. So if I dead short this, it'll read the voltage drop across my probes, and it'll show a maximum of 7 milliamps. And that's the most current that can flow through this circuit with dead short. And that's what the small current is. But the nice thing is this will also check voltage drop across a Zener diode, and it will tell you the Zener voltage. So if I take from here to here, you can see that is a 5.69 volt Zener diode. And the nice thing about it is it reads a lot higher milliamp, because even in low current it'll put 6 or 7 milliamps, whereas this thing only can do a couple of milliamp. So you can see, let's test it. I'll shut this off so I don't get shocked. And if I go from here, I don't know if I can clip it on here. We'll try to get it on there. And there's 2 milliamps, 5 milliamps, oh yeah, 10, and it'll do up to 15 milliamps. So it will do high MA also. Not as high as this one. This will go up to 40, but you can see it reads just as well. But the thing about this is this will do up to a 50 volt Zener, which is great. This is a great piece of test equipment, but it's really expensive. And if you have some of those weird high voltage Zeners that you can get them up to 75 or over 100 volts, you can't test them with that. But this one you can. And the nice thing is you can just, it's like 2 probes. You just go right across and boom, 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 and go down the line. So this is again, just a 5 volt Zener. 5.7, 5.6, 5.7 volt. So what I will do is I'm going to replace that as well, because Zener diodes have, or Zener, however you want to pronounce it, they have a tendency to drift with age. As they get older, they'll start to drift, especially after they've been running for a while and they warm up a little bit. They just don't work like when they're new. So I have some brand new ones. I'm just going to go ahead and replace it, but we didn't know what that was. That tells us what it is, and then we can actually look at the actual part number, and you'll see that it will cross over to a 5 point. Usually it's 5.2 or 5.3 volts, something like that. So let's get a 5 volt Zener or Zener, and we'll be right back. Now the reason it's important also to check Zener diodes at different forward or reverse currents is because as you draw more current through that diode, the voltage will change somewhat. So at less than a milliamp, this will not regulate at its Zener voltage. And then as you go higher in current, that Zener voltage will drift a tiny bit. Like for instance, this is like a 5.2 or 5.6 volt Zener diode, and it will drift a little bit, plus or minus a couple of millivolts, as you go higher in current. It's just the way it works. So just something to be aware of. Okay, last but not least, let's put these capacitors in. Try to get them measured out to the correct length. And we'll make sure that we can see the value of the capacitor. Alright. Definitely need to clean the flux off of this board because it's kind of messy. Okay, this one put on. Again, normally you want, I know people say you can put higher voltage capacitors, and you can, they will work. But if you go too much, they will sometimes have a problem staying properly formed. So you don't want to put, you know, a 450 volt capacitor into a 5 volt circuit, because you won't have nearly enough current and so forth, or voltage across the electrodes of that capacitor to keep it properly chemically formed. And this is just with electrolytics. I mean, that's the film capacitors don't really matter, but yes, you can go a little higher voltage. It doesn't hurt anything. Of course, the capacitance you always want to keep the same, but the voltage you also want to try to keep it fairly the same. You can go a little bit up. Like these were 35 volt caps. Now we replace them with 50s. It should be okay. Like I said, modern caps have gotten a lot better with their chemistry and so forth, and they don't have as many problems not staying formed as they used to, but this still is an issue that you need to be aware of. That's all I'm saying. So I don't always put higher voltage caps in. I try whenever I can, especially if I have them available, try to keep similar voltage. You know, maybe one notch up in voltage. You know, if there's a 10 volt cap, I may replace it with a 16 volt, and it'll work just fine. But I would not put, whereas a 10 volt cap, I wouldn't put a 100 volt cap in there, if that makes sense. There we go. Our board is complete, and I have 2 nice new fuses. Let's see here if I can find the correct ones. Let's see. T1A, yeah, these are time delay 1 amp fuses, and I want to make sure T1A, I want to make sure these are tight. Might have to squeeze them together. Nope, they're good. All right, our board is complete. I'm just going to take some isopropyl and thoroughly scrub the back of this board, and then I'm going to let it kind of self-level, because this is going to kind of liquefy the flux, take out all my fingerprints and all the uglies, and this will sit and dry, and as it dries it'll kind of level off all of the flux, and it'll make the back of the board look nice and shiny. So you can see what it's doing already. I'll just keep going across here, and the idea is you want to keep it wet and then it will, you know, this anhydrous isopropyl that I use here, it dries pretty, you know, it evaporates pretty fast. So okay, and we're just going to leave this on there and let it dry, and then when it's done, this board's going to look really good. And that's it. So I'm going to wrap this video up right here, this part, and call this part 1. And of course, as always, I wish you all peace, joy, happiness, and good health in your lives. I hope you enjoyed the little chat we had, and I look forward to seeing you in the next part that we release here. Till then, stay well and take care, and we'll see you again soon. Bye-bye.